In the last video, we talked about the second derivative test for functions of more than one variable, for functions of two variables. And let's just review that what you do is you look at this matrix, the Hessian matrix, which is the matrix consisting of the second order partial derivatives, and then you calculate the determinant. And okay, well, here's the criterion. If you have a negative determinant, you have a saddle point. If you have a positive determinant and the number on the top left is positive, then you have a local minimum. And if the number on the top left is negative, it's a local maximum. If the determinant is 0, the test is inconclusive. But I didn't explain why it's true, and then in this video, I'm going to give you some indication of why it's true. And to understand why it's true, you have to be familiar with quadratic forms and positive definite matrices, and I have some videos on that topic. So let's just talk about the single variable case, when you have a function of one variable. So often, the explanation that's given for the second derivative test for a single variable is that if the second derivative is positive at a critical point, that means that the derivative is increasing as x increases. And if the derivative is increasing, and the derivative is 0 at the critical point, then that means that slightly to the left, the derivative has to be negative, and slightly to the right, the derivative has to be positive. And that means that you have this kind of bowl-like shape. It's a concave up, and then the critical point is a local minimum. And similarly, if the second derivative is negative, then that means that the derivative is decreasing, and that means that you end up getting this upside down bowl. It's like a concave down. And then the critical point is a local maximum. But that's one way of thinking about it. And then another way of thinking about it, which actually leads to the more general result, is to use the Taylor series approximation. So let's say that this has a critical point. So f is this differentiable function, and let's say that f of x has a critical point at x equals c. Okay. And what happens is, let's take a look at the Taylor series, or just Taylor series expansion of f at c. What it's going to look like is you have f of x is approximately f of c plus f prime of c times x minus c. Now this is the linear approximation to f of x. But if you continue, then you get the second derivative at c over 2 times x minus c squared, and then plus, and then you're going to get things like the third derivative at c over 3 factorial times x minus c cubed, and then it's going to continue. That's the Taylor series expansion. Now, what happens if... So we have a point where f prime of c is 0, right? Since f prime of c is 0, this quantity here is 0. So you end up getting that f of x is approximately f of c plus, and then this whole thing here is 0, because 0 times x minus c is 0. So you get f of c plus f double prime evaluated at c over 2 times x minus c squared plus dot dot dot. Okay, so this cubed part, the cubic part here, is, I'm just moving it to the dot dot dot. So these are what are called higher order terms. because they involve taking x to the third power and the fourth power and the fifth power and that sort of thing. Well, what is this? This thing that f of x is approximately. This is a quadratic function, right? This is a quadratic function. F of c is a constant, right? It's a number, it's like 7 or something. Plus, and then f double prime c over 2, this is a constant, so this is a constant. This thing here is a constant. And then you have x minus c, and of course c is a constant, right? But the x minus c in parentheses squared, that involves the variable x. And so, you know, if you had something like negative 3 plus 5 over 2 times x minus c squared, right? That's going to be a upward pointing parabola. And if you had something like negative 3 minus 5 halves times x minus c squared, that's going to be a downward pointing parabola. Remember, what tells you if you have an upward pointing parabola or downward pointing parabola is when you have ax squared plus bx plus c. If you have y equals ax squared plus bx plus c, if a is positive, you're going to get something like this. If a is negative, you're going to get something like this. So and your a in this case, right, your a, the coefficient of x squared is going to be this f double prime of c over 2. Well, this 2 on the bottom, that's not going to change the sign. So if f double prime of c is positive, okay, then your a is positive, and you're going to get something like this. If it's negative, then your a is going to be negative, right? If you have a negative number, you divide by 2, you still get a negative number, and then you're going to get a parabola that's concave down. Okay. And by the way, part of the Taylor theorem shows that these higher order terms don't matter. So your function isn't going to look exactly like a parabola, right? Because you have these higher order terms that are kind of changing things. I mean, if you didn't have any higher order terms, then your function would just look like a parabola. It would be a quadratic function. But it's going to be a quadratic function plus, you know, something times x cubed, plus something times x to the fourth, and that kind of thing. That your Taylor series is going to be, you know, it's going to have higher order terms, but part of Taylor series theorem is that these higher order terms are not going to affect the nature of the function. So, you know, if your a is positive, okay, these higher order terms aren't going to somehow make the parabola go down. Okay, it's not going to do that. That's part of the Taylor series theorem is this remainder. It's this error bound, which is saying that you can, basically what it means is that these higher order terms are not going to really matter as far as the general shape of the function, the graph of the function. Okay, so that's another proof of why the second derivative test for functions of a single variable are true. Now, you normally don't see this in a calculus class because they don't talk about Taylor series until after. Taylor series is more like a calculus 2 thing, whereas the second derivative test is like a calc 1 thing. So yeah. Okay, but why did I talk about the Taylor series proof? It's because that's going to be used for the functions of 2 variables. So what happens is that when you have a function of f of x, y, so let's say that f of x, y has a critical point at x equals the point a, b, okay? Let's call this c, but as a vector. the vector C, which is AB, the point AB. Okay, then what happens is you can look at the Taylor series expansion of f of xy at the point C. And what it's going to look like is this. So you have f of x, but this is, x is x comma y, is equal to f of c plus, okay, partial f partial x evaluated at c times x minus c plus partial f partial y evaluated at c times x times y minus c sorry, it's not x minus c. It's if your c is a comma b, it's x minus a, and then it's y minus b. Okay, so you have this, and then the second order terms, you're going to have 1/2, and then times. Okay. The second derivative, partial x squared at c times x minus a squared plus the second partial derivative with respect to x partial y evaluated at c times x minus a times y minus b plus the second order partial y partial x at c, x minus a, y minus b, and then plus the second partial derivative with respect to y at c times y minus b squared. So this whole thing is being multiplied by 1/2, and then you have these higher order terms. So basically, it's like the Taylor series expansion of a function of a single variable. You have the f of c, and then instead of the f prime of c, you have two partial derivatives. And then for the second order terms, you don't just have the second derivative, you have 4 second order partial derivatives. And then you have higher order terms corresponding to when you take the third partial derivatives, right? You're going to have 9 of those. And what happens is when you have a critical point, right? So this is a critical point. You can take the Taylor series expansion at any point, but if you take the critical point, what's special about the critical point is that the partial derivatives are going to be 0 at that point. So this is going to be 0, this is going to be 0, so this whole thing is going to be 0. This term is going to go away, and then you have this. Now this thing here can be represented. This is where that Hessian matrix is going to come in. This is the same as taking, it's the same as what you get when you take this matrix x minus a, y minus b, you multiply it by this matrix, and then this. That's what this thing that I put in the box is. So this matrix, that's our Hessian matrix. It's the matrix of the second order partial derivatives. And this is a quadratic form. Notice that since the Clairaut's theorem tells you that f sub xy is the same as f sub yx, right? So these are the same. And what does that mean about the matrix? This matrix is symmetric. Right? This is a symmetric matrix. And this is a quadratic form. This whole thing is a quadratic form. And in the series on linear algebra, I talked about what happens when you have a quadratic form, right, that's given by the symmetric matrix. You can visualize what the graph of this is going to look like based on the eigenvalues of this matrix. And if you look at, where is it? This derivative test, okay, what's going on is if the derivative is negative, so the derivative of this, not the derivative, why do I keep saying the derivative? It's the determinant. The determinant of this Hessian matrix is the product of the eigenvalues of this matrix. So D is the product of the eigenvalues of this Hessian matrix. That's an interpretation of the determinant of a matrix. So the Hessian matrix here, these are real entries, and this is a symmetric matrix, and one of the theorems is that when you have a symmetric matrix with real entries, its eigenvalues are real. In general, if you have a matrix with real entries, the eigenvalues might be complex, but when you have a symmetric matrix, it's a theorem that the eigenvalues are real numbers. And the determinant is just the product of those eigenvalues. And when the determinant is negative, so if you have a product of two numbers and it's negative, what does that tell you about those two numbers? If you have two real numbers, you multiply them and it's negative, that tells you that one of the numbers is positive and one is negative. So that means that you have one positive eigenvalue and one negative eigenvalue. And one of the things that we talked about in the video on the spectral theorem is that if you have one positive eigenvalue and one negative eigenvalue, then your function is going to have a saddle point. And that explains why if D is negative, you have a saddle point. Now what happens if D is positive? If D is positive, then things are more tricky because it's possible that you have two eigenvalues that are positive, but you could also have two negative eigenvalues. And then when you multiply two negative numbers, you get a positive number. Okay? It's a local minimum. Your critical point is a local minimum if the two eigenvalues are positive, and you have a local maximum if your two eigenvalues are negative. Now, if you just know the determinant, you can't tell which one it is. So you need this additional criterion. And one of the things that I showed in this video on positive determinant matrices is that when you have a matrix that's like this is a symmetric matrix with real entries. If the determinant is positive, and if A is positive, A is the number on the top left, if A is positive, then your matrix has two positive eigenvalues. So you have a local minimum. If A is negative, and the determinant is positive, then you have two negative eigenvalues. And that explains why this criterion is true for the local min and local max. And then the inconclusive part, if the determinant is 0, that means that one of your eigenvalues is 0, right? And then if you have one eigenvalue that's 0, then your quadratic form is gonna, it could look something like, 2u squared, or it could be negative 3u squared, right? So you don't know what you're going to have. So the test is inconclusive. Yeah. One thing that might happen is that the third order terms might play a role. But anyway, certainly if all you know is that one of the eigenvalues is 0, that's not going to tell you anything about the behavior of the function. So now are you sure, do you understand what I mean by the 2u squared and negative 3u squared? Because by the spectral theorem, you can diagonalize the Hessian matrix, and then you might have a matrix that's like 2, 0, 0, 0, right? You have a matrix where the diagonal entries are the eigenvalues, or you could have something like this. In either case, your eigenvalues, one of the eigenvalues is 0, and then you don't know the other eigenvalue. And since you don't know the other eigenvalue, you can't say what the behavior of the function is. Okay, so that basically is the explanation for why the second derivative test is true. Again, if you don't know linear algebra to the point where you know about quadratic forms and positive definite matrices, it's not obvious at all why the theorem is true. Okay, so the reason is because, let's just review, because when you look at a function of more than one variable, you have this multivariable Taylor series, and then when you have a critical point, the partial derivatives are 0, so basically this function, f of x, looks like, this quadratic form is like the analog of a parabola, right? It's like a paraboloid. And this paraboloid, well, you might have a saddle point also. Whether you have a paraboloid that kind of goes up, or like a bowl, or an upside down bowl, that's another paraboloid, or you have a saddle point, that's going to depend on the eigenvalues of this Hessian matrix. And for a 2 by 2 matrix, there's this criterion in terms of the determinant of that matrix. This is a real symmetric matrix. There's a criterion in terms of the determinant as well as the top left number. That tells you about what the eigenvalues are. And that's basically the summary of why the second derivative test is true. Okay. So it's definitely not something that you see in most multivariable calculus textbooks that don't assume that you know linear algebra. Let me look at this book. They give you a proof, in the book that I'm looking at, they give you a proof in the appendix, but the proof is I don't think anyone can really understand that. I mean, maybe it's technically true, but it's complicated. Maybe they do give the proof using Taylor series. But anyway, that's the explanation of why the second derivative test for multivariable functions is true. And you're going to have second derivative tests for functions of more than 2 variables, right? So let's say that you have f of x, y, z. Then your second derivative matrix is going to be a 3 by 3 matrix, because you have f sub x, f sub y, and f sub z, and then each of those has 3 partial derivatives. So you get a 3 by 3 matrix, you have 9 second order partial derivatives, but the theorem is still the same. You have a local max, a local min, or a saddle point, depending on whether this matrix, 3 by 3 matrix, is positive definite, negative definite, or neither. And there's a criterion for positive definite in terms of the determinants of the matrices. So maybe I'll just say something very quickly about that. So what happens if you have a 3 by 3 matrix? So like, let's say that you had, I don't know, something like this. Is the matrix positive definite, negative definite, or neither? So you look at this quadratic form and you want to know if the eigenvalues of this matrix are all positive, or all the eigenvalues are all negative, or you have positive and negative eigenvalues, then there's the theorem that says that you can look at the determinants of this matrix. So you have this 1 by 1 matrix, right? The determinant is 1, okay, that's positive. And then you look at the determinant of this 2 by 2 matrix like this. So you look at this matrix and then calculate the determinant of that, and then you look at the whole 3 by 3 matrix and the determinant of that. Oh, maybe I'll use a different color. Look at this. And then the theorem says that if the determinants of all these 3 matrices, so you have to look at the determinants of these matrices, if they're all positive, then your matrix is positive definite. If they're all negative, then your matrix is negative definite, and if you have some that are positive and some that are negative, your matrix is indefinite. So in this case, if you look at the determinant of this one, the determinant is 1. The determinant of the second matrix is 3 minus 8, that's negative 5. So you have a positive determinant and a negative determinant, so this matrix is indefinite. This is kind of a neat criterion for positive definite. You don't have to find the actual eigenvalues of this 3 by 3 matrix, you just need to calculate these determinants. So it's a very useful, handy criterion. Okay. So that's all I wanted to say in this video. Thanks.